This is Math 139, Section 1.1, Part A. We're going to be looking at what constitutes a mathematical function and some function notation here. And hold on, let me get that distraction out of the way. There we go, turn my volume down, sorry. All right, so we'll begin by looking at a mathematical relation. It's simply a way of defining two variables dependent on one another. As we discuss our definitions, I'm going to put them all into the same context, just for comparison purposes, by considering the correspondence between U.S. presidents and the years in which they were elected. So in the context of our definition, our two variables would be the election year. Maybe I'll call that E for election year. And the president that was elected. We'll call that P. In any relation, one of our variables is designated to be independent, and the other one eventually we'll call dependent. Sometimes we think of the independent variable as the input variable. So IN, independent, IN, input. Or in other words, the variable for which we choose a value. The set of all possible values of the independent variable is called the domain. So in our example with the U.S. presidents, for now, let's designate the election year as our independent variable and find the domain. So the domain would be the set of all possible election years. And I'm going to have to admit that history is not my best subject, so I'm going to probably have to fudge just a little bit here. But I do know that the most recent election year would have been 2016. And if we go back to 2012, 2008, 2004, and so on, back to 1900, 1896, and so on, back to whatever the first election year really was. And I honestly don't know the answer to that, so I'm going to go with 1776, even though I think it was a little later than that. But that's the domain, the set of all possible input variables. The other variable in the relation is called the dependent variable. That's the output variable, or the variable whose value depends on what value we choose for our input. And the set of all possible output variables is the range. So if I was using the election years as my domain, then my range would be the set of all U.S. presidents. And of course, I'm not going to take the time, nor could I probably name them all. However, we can at least get started. I'll start from the most recent on back. So Trump, Obama, Bush, Clinton, so on and so on, right? All the way back to Washington. So again, domain, all the possible inputs, range, all the possible outputs. If I give you an election year, like 2016, you would tell me the output is Trump. All right, using that concept of inputs and outputs and domain and range, we're going to make a really important definition, mathematically vital definition. The idea of a function. A function is a relation for which each value of the input or independent variable is associated with exactly one value of the dependent or output variable. And it's this idea that it can be exactly one that's so important. In our examples with electing U.S. presidents, we want to think about whether or not that relation was a function. In fact, I'm going to say yes, and the reason is this. If I give you a particular election year, there was only one president elected during that year. And there are no exceptions to that, right? If we say, for example, the year 2016, that's our input. Then the president, our output, would have been Trump. There was no other output for that year. 2012 as our input, there's only one possible output. Obama. Right? 2008 as our input, again, just one possible output. Obama. Notice that it's okay to have the same output twice. That's perfectly allowable. It's just that for each input, there has to be a single unique output that goes with it. We could now say, using our vocabulary, that the president is a function of the election year. That is, the dependent variable is a function of the independent variable. All right, let's ask ourselves a related question. What if we switch the roles of the independent and dependent variables? What if I'd like to ask the question, is the election year a function of the president? So by asking the question this way, I've now said, let's use the election year as the dependent variable and the president as the input or independent variable. So let's jot that down. The independent variable is now the U.S. president, and the dependent variable is now the election year when we elected that president. Let's try to make our little chart again. Our input is the president. And the year is our output. If I choose Trump as the input, then the year that he was elected would be 2016. And so far we're doing fine. One input, just one output. But what happens if I let Obama be the input? Now I've got a problem because I don't have a single election year as my output. Right? I could be either referring to 2012 or 2008. And we don't know which was the correct output or which is the output we meant for Obama. This means that what we have here is not a function. For a function, every input should have just one output, and that clearly didn't work here. So this is not a function. Okay? So that's the difference. If every input leads to just one output, we have a function. If some inputs lead to multiple outputs, we do not have a function. All right, functions, or actually relations in general, can be described in a number of different ways. We can describe them verbally, using a description, which is what we just did with the presidents and the election years. We can describe them numerically using a table or a mapping diagram. A mapping diagram is the little diagrams that I was making with the arrows. We can do this analytically using an equation or graphically by literally drawing a graph. So, in each case, determining whether a relation is or is not a function requires that we start by identifying our independent and our dependent variables. We'll do that in the next several examples. So in example 2, Consider the relationship between our variables w and z, defined by this equation. W minus z squared equals 0. Is w a function of z? Again, remember our vocabulary and our phrasing. This means that we're treating w as the dependent variable and z as the independent variable. And let's just try it out. Since z is independent, I'm going to choose values of z, and I'm going to see what values of w, the dependent variable, I get. And we'll just go ahead and make a few up. Let's say that z is 1. Well, I'm going to do my math off to the side here. Looking at my equation, w minus 1 squared equals 0. Just says w equals 1. So far so good. I had one input, I only led to one output. Let's try a couple more. Let's do a z of 2. Again, coming back to my equation, w minus 2 squared equals 0. W minus 4 equals 0. So w equals 4. Still doing okay. I chose one input, and it led to just one possible value of the output or dependent variable. I'm going to do one more. Let's try negative 5. If I have w minus negative 5 squared equals 0, that would be w minus 25 equals 0, and w equals 25. Oops, I don't know why I wrote 24 there. How about 25? All right, so based on all the numbers that I've tested, it does appear that every input has just one output, and I'm going to conclude that I think this is a function. Now, I will point out that it's not possible to test every single possible value of z, so what I'm doing is kind of establishing a pattern. If I thought maybe there was something that would break that pattern, I would have tested that number, but I don't see anything that's telling me that that might happen here. All right, same equation, w minus z squared equals 0, but now I want to do it the other way around. I want to ask the question, is z a function of w? So now notice that we're being asked to treat z as the dependent variable and w as the independent variable. I'm just going to rewrite my equation down here so we can see it on the screen. It was w minus z squared equals 0. So let's see. This time I'm going to choose values of w, my independent variable, and then calculate the values of z, my dependent variable. And let's just go ahead and let's start with 4 for w. Again, I'm going to do my math over here off to the side. If w is 4, I have w is 4 minus z squared equals 0. So 4 equals z squared, and I'm already seeing a problem. There are two numbers that I can square and get an answer of 4. Positive 2 squared is 4, but negative 2 squared is also 4. So here, z could be either 2 or negative 2. I've already shown that this is not a function because I've got an input with more than one possible output. So I don't have to test anymore. All right, so that was an example of an equation or a relation that was defined using an equation. Let's look at a couple of others to wrap up this part. Sometimes the roles of the independent and dependent variables are actually defined rather than the wording, just by the format, and a mapping diagram is an example of that. Everything on this side would be part of the independent variables. This is the domain, in fact, in this set. And over here we have the range, all of the dependent variable values. We'd like to know whether it represents a function, and I think you can probably see pretty quickly that it does not. The problem's not with the 2. The input 2 has one output, 0. The problem here is with the 4 again. The input 4 has 2 possible outputs, both 1 and 2. So this is not a function. The input 4 has 2 outputs, 1 and 2. In example 4, we have a relation that's defined by a set of ordered pairs. In these cases, the first entry of each pair, we usually consider those the x values, would be the independent variables. And the second entry, what we usually consider the y values, would be the dependent variables. So we can think of these as in the form xy, where the x's are independent and the y's are dependent. All right. Well, in this case, I'm seeing the input or x value of 1 goes with the output of 4. And 1 is not used as an input in any of the other points. So the input 1 has just one output, 4. That's true for all of my other inputs as well. Notice each input, the 2, the 3, the 4, and the 5, are used only once in this list, and therefore they don't go with 2 different outputs. So I'm going to say yes, this is a function. The last example in this page, or on this page rather, is a graph. So we've got a graph of a relation, and we'd like to know whether it represents a function. In order to answer that question, I'm going to pick an x value and see how many y values I can find that go with it. Let's just start with x equals 2. If x is 2 right here, on the line x equals 2, there's exactly 1 point. Y happens to be 1 there. So that input of x equals 2 has just one y value. What if I pick x equals 0? If x is 0, again, there's just 1 point on the graph that goes with x equals 0. Happens to be a y of -1. In fact, it looks to me like that's going to be true no matter what x value I select. There'll always be just one y value, 1 point on the graph, that goes with it. So I'm going to see yes again, this is a function. You may have been taught in the past that there's a test that you can use to determine whether a graph represents a function. It's called the vertical line test. And if we use the vertical line test, basically what it means is that we could take a vertical line and we can go left to right, pass that vertical line over our graph, and no matter where we stop, we'll always hit just 1 point on the graph at a time. So if I were to stop right here, I would hit just that point, for example. No matter where I draw my vertical line only hits 1 point at a time on the graph. If you are determining whether or not a graph represents a function, it's fine to say yes because of the vertical line test. That argument, however, can only apply to a graph. You can't use that as a reason for any other type of relation. All right, that's the end of section A. We'll come back for section B in the next video.